Hello, I want to talk about the material in our next chapter, which is on really formation of images with mirrors and lenses. And I just see it as formation of images through reflection or refraction. I'm not going to go through the same kind of detail as the text does. There's a section in particular that goes through a lot of the details of image formation via refraction. And you can take a look at it and read through it. There's a lot of geometry involved, but I'm going to skip that. I'm going to really focus on the basics, the basic ideas that you need to know to determine image formation either with a mirror or a lens. I want to first talk about the types of images that can be formed with mirrors and lenses. And really, when an image is formed by a mirror, it is formed by reflection, and when an image is formed by a lens, it is formed by refraction. And we categorize the images that are formed by lenses and mirror as either real or virtual. When you form an image by reflection and the image appears to be in front of the surface, we call it a real image. The rays will actually go through the image, and you can project that image on a screen. And this effect is used by magicians to create optical illusions. When an image is formed by refraction, the image appears to be behind the surface. It's on the opposite side of the object. That's called a real image. And again, the real image can be projected on a screen. Our eyes form real images on our retina. That's an example of real image formation. When you form an image by reflection, and the image appears to be behind the surface of the mirror, then that image is called virtual. It looks like the light's coming out of the surface. The rays do not pass through the image. And examples of this are the mirror in the bathroom that you see yourself in the morning, the rear view mirror in your car, and the images that you would observe with the convex part of your tablespoon. Now, when an image is formed by refraction and the image is on the same side as the object, that image is called a virtual image. Now, the light appears to be on the same side as the object. They don't pass through the image. You cannot project that on a screen. The magnifying glass is an example of image formation by refraction that produces a virtual image. Your corrective lenses, whether you're nearsighted or farsighted, produce virtual images. You cannot project them on a screen. However, if the light from the virtual image can pass through another lens or through a mirror, it can still form a real image from that. In the case of the magnifying glass produces a virtual image, but the lens of your eye will produce a real image on the retina of your eye. Let's talk about plane mirrors. That's the most basic type of optical element that forms images. And the plane mirror forms images via reflection. The plane mirror always produces a virtual image. And it turns out the image and object distance are equal. The image and the object have the same size. you can think of the plane mirror as a spherical mirror with an infinite radius. It's really a special case of a spherical mirror. Now, the mirror, when you look at something in a plane mirror, it looks like the right and left side are reversed. Actually, really what the plane mirror does is a front-back reversal. It's like if you take a transparency, you write on it and then look through the back of it. That's what the plane mirror does. So let's take a look at how a plane mirror forms an image. And we're going to use this as the basis of what we call ray tracing. A lot of what we do in this chapter will involve us doing a ray tracing. And the ray tracing will allow us to figure out where an image is formed by an object. So I'm going to go to the board, and I have basically the same drawing as you see on the screen, and I'm going to do what's called a ray tracing of this system. So I have the mirror here and I have the object here, and I want to do a ray tracing for this. So this object has all sorts of light rays hitting it. All right, there's light coming in all directions off the object. And if I'm very judicious and picking out the rays, certain rays that hit the object and also scatter off the object and goes to the mirror, I can figure out a way to determine where the image is formed. So let's consider a ray that hits off the top of the object at some angle, comes in like this. This is an incident ray. And so that's going to bounce off the mirror. So let me draw normal to the surface. And that ray is going to obey the law of reflection. So this angle of incidence, which I'll call delta, will get reflected. I'll try to draw it as best I can. That's the reflected ray. Hopefully these are almost the same. I'm trying the best I can to make them the same. And just for fun, I'm going to take this ray and just extrapolate it back behind the mirror. Okay? So that's one ray. But one ray is not enough to tell you where the image is at. You need at least two rays to tell you where the image of this point is at. So let me take another ray that comes off the top of that object and scatters off in a different direction. So let me draw this ray. It's red. It hits the mirror there. Let me draw the normal to the surface. And we'll call this angle of incidence theta. And of course the angle of reflection is also theta. Let me do a better job drawing that. And these reflected rays really kind of scatter out in all directions. However, if I take this reflected ray and extrapolate it back behind the mirror, they cross at this point. Where they cross at that point, that's where the image is of the top of the object. And so I have found the reflection of the top of the object right there. Oops. Let me find a color that works. And if you do it on paper and you do it to scale, you will find that this distance and this distance are equal. How can I prove that to you? Well, let's look at this purple triangle. I mean, this one right here. This angle's delta. This angle's 90 minus delta. Well, what about this angle? This angle's delta. This angle also is 90 minus delta. All three angles here in this triangle and all three angles in this triangle are exactly the same. That says they're congruent. That says they're similar. However, they both have this side in common. So the three angles are the same in the two triangles, plus they have this side in common. That makes them congruent. That means that they're the same triangle. That means that this distance and this distance are the same. So that the image distance and the object distance are the same. The distance from the tip of the object to the mirror is the same as the distance from the tip of the image to the mirror. Now let me say something about the line of sight. Now you can actually have another ray that comes off here and gets reflected. In fact, if you look at the extreme case, let me use blue, a blue marker, where a ray gets reflected off in that direction. It's supposed to be a straight line, sorry. Let me do a better job. That could also be another ray that's reflected off the mirror. Okay. As long as you are in here, in this region, you will be able to see the image of the object. As long as you are in this region, as long as your line of sight is in this region, you will be able to see the image of the object. If you're over here, no light rays will come to you from that point. And so when you're over here, you will not see the image of the object. You're outside of the range, really outside the line of sight. And so you won't be able to see the image from over here. You will only be able to see the image of the object if your line of sight is in this region. Line of sight is basically the line for which the rays can come towards your eyes. Okay, let me show you another example involving image formation with mirrors. Here's an object that's in front of two mirrors that are perpendicular to each other. How many images are formed? It turns out that you'll have one object and three images. One of the images involves a secondary reflection. The one object, or the one image that's back here on the opposite corner, that involves two reflections. And it'll look just like the object. The ray tracing for this is quite complicated. So if you have a 90-degree angle between the two mirrors, you can get three images. If you have a 60-degree angle between the mirrors, you can get 5 images. The smaller the angle, the greater the number of images. Of course, the ray tracing gets much more complicated as you make the angle smaller. You should think about how many images you'll see when the two mirrors form a 120 degree angle. Let's consider another example. And this is an interesting question. What is the minimum height of a plane mirror that's required to see an image of you? It turns out that you only need a mirror that's half your size to see your entire body. Let's see how that works. Let's say I have a mirror here. There you are standing in front of the mirror. It's a flat mirror. So if you stand further back, all it's going to do is change these angles. So imagine the light coming from your feet, hitting the mirror here, and then going into your eyes. This angle theta and this angle theta have to be the same because of the law of reflection. Because of that, I can remove this mirror. I can remove this bottom part of the mirror. I don't need it. I can see my feet by removing, if I still remove the part that goes from B to A. Okay? Now, let's look at in between my eye and the top of my head. I can do the same, I can make the same argument with light coming from the top of my head, hitting the mirror and bouncing into my eye. I can remove the upper half of mirror DC. So if I remove the upper half of DC and I remove BA, I've essentially removed half the distance between A and D, half my height. So if you have any questions regarding this is always puzzling. If you have any questions regarding this, please ask me. But all you need is a mirror that's half your height. No matter how far you are away from the mirror, you can see your whole body. Let's do one more example. In this example, and which I took from a website, the link is listed below. I don't know if that link's still valid. I took this many years ago. I have 6 people in front of the mirror. And the question is, who can see who? We just got to consider the line of sight. For example, who can Abe see? And I've outlined a line of sight for Abe. Look at the line of sight of the rays coming towards Abe. Abe can only see the images of Eva and Flo. Bev, if you draw the line of sight here and there, Bev can see Don, Eva, and Flo. And then you draw the line of sight for Sis. Sis can see herself, Don, Eva, and Flo. Then you draw the line of sight for Don in between the mirrors, one there and one there. Don can see Bev, Sis, Don, Eva, and Flo. And if you look at Eva and Flo can see everybody. And again, all you got to do to answer that question is to look at the line of sight that each person has in the mirror. And again, the line of sight indicates the light that comes from the image. Notice this arrow is right. If you look at Abe, this is the line of sight Abe has. Sorry, this is a ray that's reflected into Abe's eyes. Okay, I want to do one more example. This example is not in your notes. Suppose I have two mirrors that are perpendicular to each other. And what I say here is going to only be true if the mirrors are perpendicular to each other. So let me draw the two mirrors. This is a 90-degree angle. And I'm going to have a ray of light hitting on the surface there. Let me draw the normal to the surface right there. And let's call this angle theta. That ray is going to get reflected at the angle theta. And again, I'm drawing this by hand, but if you do this with a ruler and a protractor, it comes up perfect. So this is the angle theta. It hits this mirror. And again, it's going to bounce off at what angle? And what angle is that going to bounce off at? Let's see. If this is theta, that's a right angle. Let me grab a marker. This angle up here is 90 minus theta. This angle's theta. And so the angle in here is 90 minus theta. And so what's going to be the angle of reflection? 90 minus theta. Well, if that angle is 90 minus theta, this angle is theta. Now think about it. Look what the ray does. It comes off in the opposite direction. So the ray comes in at this angle theta. It goes out at the angle theta. So as long as that's 90 degrees, when you have light bouncing off two mirrors that are 90 degrees apart, this ray is going to go off in the opposite direction. Okay. Comes in at the angle theta, goes out at the angle theta, as long as this is 90 degrees. This gives you an example of how much geometry you have to do with geometric optics. And again, we're treating light as a ray. We're treating light as a particle as opposed as a wave in these two chapters, chapters 35 and 36.